This is our 5th computer session, and by the end of this one, we will have our fully functional one-dimensional finite difference time domain code. In the last computer session, we'll add a device to it. Let's remember where we were. Let's run step 4. And what we did was a one-way source. We added our perfectly absorbing boundaries so that pulse goes away. What apparently is getting reflected, if we look at the scaling, is actually very, very small. What's missing here is learning from this. How much power is being transmitted? How much power is being reflected? How do we add that calculation? And that's the focus of this 5th computer session. So we'll change this to step 5. Save it. Whoops. And we'll change our comment here rather than add total field scatter field source, which we did last time. Now we're adding reflectance and transmittance calculation. So at this point, we're doing everything the same in terms of initializing the units, the constants. We open a figure window. But now we need more source parameters because we're calculating transmission and reflection probably over some span of frequencies. And we want to plot reflection versus frequency. So let's come up with an array of frequencies for which we want to calculate reflection and transmission. We'll use the linspace command. We'll go from 0 to f max. And the third input argument here is how many frequency points we want. So let's control this with a parameter nfreq. And let's set this to 1000. And this is one of the huge benefits of finite difference time domain. If we were developing a frequency domain method, we would have to run this 1000 times to get all those frequency points. Here we can run a single simulation and get all 1000 frequency points from it. So we're generating 1000 reflections and transmission numbers over the span of frequency from 0 to 5 gigahertz. So we've modified our dashboard to do that. Now we have to go down into where we're computing the source. And what we want to do, we want to inject our source right at the start of the grid. And I'll go one cell over, and that gives us the first cell to record reflection, and in the second cell, we're actually injecting our source. And this gives us, by moving where we inject the source way over to the left-hand side, it gives us the entire grid to build in our device and to look at other things. So it makes sense to do that. That's the only modification to the source. The next thing we have to go down to is where we're initializing our fdtd parameters. Remember, the finite difference time domain is a time domain code. If we want to plot something versus frequency, these are frequency domain concepts. We're going to have to take some Fourier transforms. And in the theory slides, we talk about how to do this efficiently. And so we're going to calculate the Fourier transform sort of in real time as this thing is running. But we got some things to initialize. First is our kernel, or kernels. There's one kernel per frequency. So remember, freq is an array containing the frequencies that we're interested in. And then this complex exponential ends up becoming the Fourier transform kernel. So k is an array, 1 for each frequency that we're interested in. Now we'll initialize the arrays where we're storing each value of reflection and transmission for each frequency. So ref will set to all zeros, and there will be nfreq of those, 1 for each frequency. TRN for transmittance will do the same thing. And we'll need something else. We'll need to do the Fourier transform for the source. Remember, the spectral content of the source rolls off because it's a Gaussian source, and we don't want to mistake the roll-off in our reflection or transmission for the roll-off simply because there's less power in the source. So we will divide those Fourier transforms by the Fourier transform of the source. That makes the source look as if it was unit amplitude at each frequency. So that's it. We've initialized our Fourier transforms, the kernels, and the places where we will store those Fourier transforms. Next, we need to go down to the main loop. And at the very end, before we show the status, but after we've done all of the business, this is where we'll update our Fourier transforms. We have all new fresh field values. And we'll update our Fourier transforms from them. We set up a loop and we go over each frequency. So we will update our Fourier transforms at each frequency, so we set up a loop to go over each frequency. So what we're doing here is we're looking at the electric field at the first point, and we're integrating that over time. And we do that integration one for each frequency. And we'll do our transmittance the same way. However, since we're injecting our source from left to right, we record our transmittance at the far side of the grid. And we need to be Fourier transforming our source as well, so we can divide by it to normalize out. And here we'll just use E source at time t. So that's it. That has done our Fourier transforms. Now what we want to do is come to the outside of the loop. Once we're done, we have our Fourier transforms, but we need to divide by the source to finish normalizing it. So maybe we'll say, I don't know, normalize Fourier transforms to source. So we'll say ref is ABS ref dot divided by source. Our Fourier transforms are amplitude quantities, so we'll divide by source, but then take the absolute value and square it to get reflectance. And we'll do the same thing for transmittance. And now we have reflectance and transmittance. What I like to do, and it's always good practice, is add these together. We have not built loss into our model. So if we add reflection and transmission together, we should get 1. So that's called conservation of power. So let's calculate our conservation. It's just ref plus TRN. So that's it. All the code is there. We're going to add 2 more things. Later, the last thing we'll do is add a nice pretty plot of reflection and transmission. I'll step you through that. But I like to watch those Fourier transforms evolve as the simulation runs. So what we'll do is we'll go back into where we're displaying the status and add some code in there to do that. All right. So we're going to say subplot 11, 1, 1 to 4. And then so we're setting up a subplot, so we'll have something on the top and something on the bottom. And the reason I'm doing this 11, 1 thing is I'm just controlling the spacing within the subplots. You could try a simple, let's do it at first. Let's do a simple 2, 1, 1. And we'll see what it looks like, and then we can fix that. Okay, so we show the fields in the first subplot, and then we will show ref and TRN in the second plot. Subplot 2, 1, 2. That's the second subplot. Now, remember, outside of this loop, we had to divide by the source, take the absolute value and square it, really to get a meaningful reflectance and transmittance. So we're going to have to do this inside of our loop before we can even display them. So let's just call this a temporary normalization. And we'll just call it R. Yes, ref dot divided by source squared. And the same thing for T. So in this case, R and T are taking the place of what we'll eventually call ref and TRN. But we don't want to overwrite them here because ref and TRN are our Fourier transforms right now. So we had to come up with new variable names. Okay, so that's our temporary calculation of reflectance and transmittance. And those will be what we plot. So we want for the frequency axis, that's our array of frequencies. And we'll plot our temporary reflectance calculation. We'll make that a red line. Then we'll say hold on and hold off while we plot these other things. Let's plot our transmittance. We'll make that a blue line. And then I also like to plot the conservation. So we can do it really easy, just R plus T. And we'll make it a dotted black line. Let's set our axis limit so it's not constantly rescaling on us. That can be irritating. We want to start at the first frequency.